for photovoltaics is checking the cost of the solar energy. And in this figure, we can see clearly that the price of the solar energy has decreased a lot these last 10 years, being right now very competitive with the fossil cost with most of the fossil cost ones. So right now, solar energy is really competitive, and this is very good for a massive deployment of photovoltaics. Okay, when we talk about photovoltaics, we have easily in mind these photovoltaics fields. No? Also, we have in mind these solar panels, typically we can see in roof in houses. No? So this is very nice, and it's well done by silicon material. No? And in fact, these modules are mainly based from silicon. But there are a lot of novel applications where silicon is not very well suited. And in particular, there are a lot of needs, and especially from architects, but not only from architects, also from electronics, that will require integration of photovoltaics. This is, here we can see some examples. So there is basically needs of flexible photovoltaics, and this is not possible currently with silicon. There are also needs of a certain degree of transparency, and this is, okay, this can be done more or less with silicon. I will come back later to that, but it's not the best material. And then there are also a need for low power photovoltaics, because all the rest mainly relies on high power, and there are many small electronic products that require low power, such as lights, as we can see there, or road panels, also IoT sensors. No? IoT for Internet of Things, for connected sensors. So when we talk about photovoltaics, in fact, depending on the materials used, we talk about several generations. First generation relies mainly on silicon materials, on silicon solar cells, as we can see there. There, the second generation, which relies on thin films, and this is the topic of my talk today. And so thin films are very interesting. I will come back to that. And we can find them commercially available. We can buy them. It's not so easy as buying a silicon panel, but we can find them. And mainly we can find cadmium telluride, not really here in Europe, but we can find them in US, for example. And we can find also CIGS, which is a compound of copper, indium, gallium, sulfur, selenide. Then there is the third generation PV, which is mainly with organic and perovskite materials. And so this is very nice because perovskite, for example, has demonstrated recently very high efficiencies. But there are still many problems with these materials, especially of stability. And in any case, these are really at the research lab. For the moment, there is no commercial product available from this material. So the main advantages of thin films is principally the few material need. For example, the active layer in a thin film device is typically around 3-4 micrometer thick. So this is very few material in contrast to silicon. Then also the fabrication process of thin film device is usually very simple, at least compared with silicon, because silicon relies on a clean room facility, and this is quite expensive. Also, the production cost of a thin film solar cell is very cheap, again, compared with silicon. But the main advantage is the easy integration in any kind of substrate, and especially in low-cost substrate. So a thin film solar cell can be integrated in almost any kind of substrate, such as glass, metal foil, or a polymeric foil. Also, if we look at the efficiency achieved by thin films materials, here we can see for CIGS and cadmium telluride, we can see that, in fact, right now the efficiency is a bit higher. It's around 23%, so we are getting close to the efficiency reached by silicon solar panels. So this is also good news for the thin film technology, which is approaching the silicon efficiencies, but at a lower price. Okay, then there is something important to have in mind, but this is true not only for here PV technology, but it's true for any kind of technology. No? It's very important, at least I think the message has to come from our side, from the researcher, but it's very important to try to work on earth abundant material, no? Materials which are abundant in the crust, the air crust. No? And in that sense, the European Union has defined critical raw materials, and this is based not only on the abundance, but also on the economic importance and supply risk. For example, antimony is a very abundant material in world, but it's mainly extracted from Asia, and so it's, at least it is seen as a critical raw material from Europe. No? So if we look at these materials, we can see that gallium, indium, and tellurium, so which are forming the CIGS, the chalcopyrite, the copper, indium, gallium selenides, and the cadmium telluride, are critical raw materials. So this is not good for in case of a massive deployment of this technology. No? So we need to explore materials based on earth abundant elements, and ideally also with non-toxic elements. So if we look at the literature, which are the current CRM-free, so critical raw material-free PV technologies, here we can see in this table the different materials we can find and which have been fabricated into solar cells. So some of them giving very good efficiency as this copper sulfide, but we see that the best efficiency in all the cases are achieved with this family of material, which are the Kisterite. Kisterite, which is formed by copper, zinc, tin, and selenium, and O sulfide. So why these Hysterite are also so interesting, apart the fact they have formed from earth abundant element? One thing which render them really interesting is the structure. The structure, the tetragonal structure, as we can see there, so copper tin planes, copper zinc planes, and in between the anion, the chalcogen being incorporated. This structure is very similar to the CIGS and the cadmium telluride structure. And this is very important because currently there exists production line based for CIGS and for cadmium telluride. So in case of a demonstration of a very high efficiency with Kisterite, this is very good because since the material, the Kisterite structure is very similar to the CIGS and the cadmium telluride one, the transfer from the lab to the industry is quite an easy task. And this is very important for this material. Okay, other advantages of Hysterite is that they have formed from low toxic and earth abundant element. We have said that. They have also naturally a p-type conductivity. There are intrinsic defects that render this material naturally p-type. The band gap is direct with a very high absorption coefficient, and this is perfect for solar cells. And there is also one criteria which is very interesting, and is the tunability of the band gap. The band gap can be tuned depending on the composition, okay, mainly on the anionic composition, but also on the cationic composition. We can replace, for example, copper with other materials, with other elements, and the band gap can be tuned. Okay, but this material, it's not perfect for the moment, because since it is formed from many elements, finally, many defects can be formed. And in particular, for example, copper and zinc are isoelectronic elements, so they substitute themselves very easily, and there is formation of anti-side defects, copper on zinc and zinc on copper, which are very easy. Tin also is very volatile, and it has a tendency to be lost during the thermal annealing, during the formation of the Kisterite. Tin is also a multivalent element, and this is probably the most, at least the main reason advanced until now for the low efficiency achieved to date, no? Because, yeah, there have a lot of formation of defects related to this multivalence of tin. Also, tin has a strong tendency to interact with the alkalis, and naturally, since at least in most cases, this solar cell is directly grown on a glass substrate, glass contains alkali, and it could be contain sodium in particular, and sodium can be problematic if we don't control the quantity. Okay, zinc is also a relatively volatile element. So all these defects that can be formed are more or less the main reason why the efficiency is not increasing so much until now, and explaining the VOC deficit. If we look at the literature, all the best results achieved with different composition, here with different selenide materials, with sulfoselenide, and even by substituting with other elements, so with other cations, all of them finally have still a large VOC deficit. Very recently, in fact, a couple of years ago, in this paper, Aaron Walsh group demonstrated that it seems that the VOC deficit will come from tin on zinc anti-site deep defects, which are created with these structural defects. And these create giant recombination traps. And this could explain the low VOC observed to date in all the Kisterite devices fabricated. So there are currently several strategies to avoid these tin-related anti-sites, and we are currently working in the partial substitution of tin by germanium, and also on doping with hydrogen. In fact, this was also advanced in the paper of Aaron Walsh. But there are so many things we can learn from CIGS, the cousin material. If we look, for example, in this graph showing the efficiency as a function of the band gap, we can see here the selenide, the pure selenide chalcopyrite and Kisterite show an efficiency difference of 2%. If we see the pure sulfide side, so the high band gap side, we see that this difference is even lower, 1%. But here in the middle, we can see a large difference of more than 10%. And in fact, here for chalcopyrite, it was in past demonstrated because during many years, the efficiency was not increasing also. But here, at the end of the 19th, beginning of the end of the 80s, beginning of the 19th, they started introducing gallium in the chalcopyrite and also introducing alkalis, and they achieved very high efficiencies. So we strongly believe also for Kisterite that the key could be optimizing doping and alloying, but by selecting or by finding the best possible materials. So here in this figure, we can see the typical structure of a Kisterite or chalcopyrite solar cell. So it's exactly the same. We replace the absorber, the CIGS absorber by a Kisterite one. You can see the back contact, the front contact, and here an SEM image showing the different layers. Okay, here in this slide, we can see the entire fabrication process with all the different steps. All of them can be done in a lab without any cleaning condition required. I mean, there is no need to make them in a clean room, for example. And here in this figure, we can see, so here an image of a solar cell, okay, of a sample with several solar cells here with anti-reflective coating. In fact, this sample was the best we fabricated at IREC, and it was giving an efficiency of close to 12%, as we can see there in this current voltage characteristics. Yeah, this figure is just to show that finally the active area of this solar cell is very small. It's something less than 5 microns, as we can see there. And it's quite amazing if we compare, for example, with a human hair, that energy can be produced from a so small area. No? Okay, another advantage of thin film materials, and in particular of chalcogenide thin films, is the tunability of the band gap of the absorber. So this is possible with Kisterite, with chalcopyrites, and with also many other chalcogenide absorber, which involves sulfur and selenium, and also telluride. So this band gap tunability is particularly interesting when it is combined with transparent back contact. So this is interesting because it allows the fabrication of new kind of devices which are not feasible, for example, with silicon. And we can fabricate semi-transparent devices, you can see there with a transparent back contact, which are also bifacile devices, which can be illuminated from front and back. And also the development of wide band gap absorber allows the integration of two cells in series, so a wider band gap cell and a low band gap cell stacked together. And this is called a tandem architecture. And this is currently a strategy followed by the silicon industry as a way to increase in a cheaper manner the efficiency. So at IREC, we have worked with wide band gap materials, with chalcopyrites, with kisterites. So here in this table, we can see the state of the art of several cells fabricated worldwide, and here some cells fabricated through a Spanish national project. So we got interesting results both with Kisterite and with chalcopyrite, and here we can see in this picture So several wide bandgap CIGS absorber with different compositions. Here we were varying the anionic compositions. Here we can see the absorber. So here the selenium, the copper gallium selenide absorber, and the copper gallium sulfide absorber. For this absorber, we demonstrated an efficiency close to 5%. In fact, it was 4.4, 4.5, I don't remember right now. And for the copper gallium sulfide, we demonstrated an efficiency close to 1%, a bit less. So that's interesting because, as we can see there, this absorber shows a certain degree of transparency. Also, we work in another project, in Master PV project, which is from the Solar Aeronet Call. We work on other ways of getting transparency, this time not by tuning the bandgap, but more or less using the same strategy followed by the silicon, which consists on having transparent areas separating the different cells, as we can see there. So this is a CIGS mini module we fabricated in collaboration with a group in Halle in Germany. And we got from this module an efficiency close to 13%. With this one, I think it was around 20% transparency in the visible range. So this is a very good result, and currently it is under monitoring in the rooftop of IREC. So we have seen that with these chalcogenide thin film materials, we can get a new application, as we can see there, and which are already being commercialized, especially with CIGS. We can see in this picture directly, so modules directly integrated in the facade of a building. We can find also flexible CIGS modules, which can be integrated directly in roof with tiles which can be curved, or here directly integrated in metallic roof also. So they are interesting for building integration, but also for other applications, for automotive integration, for product integration, as we can see there are some examples. For IoT sensor also, they are very interesting. For semi-transparency, as we can see there. So here we see, okay, here there are modules of amorphous silicon, because CIGS for the moment it's not being investigated in that sense. And here we can see the semi-transparency achieved by the silicon. So with transparent areas separating the silicon cells here, and which is giving a kind of transparency. But this is not really appreciated. This is not very appreciated from architects, because it induces inside the building a kind of shadowing depending on the sun situation, no? The sun position moving during the day. So yeah, we can find also semi-transparent devices from organic solar cell, but with problem of efficiency and stability. So in conclusion, the Kisterite are an emerging technology which is still at the lab level, but with a high potential for sustainable mass deployment, and especially because it is formed from earth-abundant elements, and also they have the potential to reduce cost of solar energy production. But there are still many challenges before seeing one day a Kisterite solar panel. Currently, we are leading, IREC is leading a project on Kisterite, which is called Customart, and which aim to demonstrate 20% efficiency with this material. So wide bandgap materials, CIGS or chalcopyrite, Kisterite, or other chalcogenides are also another emerging technology still at the lab level for the moment, but with a high potential for integration of photovoltaics in building, in windows, with semi-transparent windows, for example, or in tandem architectures. So there are still many challenges, but there are very expectatives, especially in these wide bandgap materials. In fact, the research is moving towards these wide bandgap materials because they allow novel applications which are not possible with silicon. And this is the main, or at least this is currently the main advantage of these thin film chalcogenides materials. So that's all from my side. Many thanks for your attention, and thanks from my colleagues from IREC and UTC.